and even more important, and that's whiskey. So everyone give a hand for Jim.
So who wants to learn how to make whiskey with JavaScript? Who wants to just go drink some whiskey? Actually, all right, we got to get this done. All right, so thank you guys for coming today. We're going to talk about Node.js and whiskey. A bit of background about myself. By day, I'm a CTO at a company called Bug Labs. We build services and products for the Internet of Things. A couple of them are listed up here, Dweet.io and FreeBoard.io. We're actually going to get a little demo of them later, not for blatant placement, but actually it has something to do with what it is we're talking about today. And then by nights and weekends, I distill alcohol. And before you think of the nefarious things that might go on, actually it's legal alcohol. My family and I started a distillery in late 2010, and my mom and dad essentially run the distillery during the normal business hours, and then I help them out on the nights and weekends and anything I do to help them out. We make good shit. Our liqueurs actually are the highest rated in the United States right now. And we're also making whiskey, but I don't have any ready for you yet because it takes a long time to make whiskey, so you'll have to wait for that fun part. I love my job. I actually probably maybe could say I'm the only person that actually gets to drink the output of my code, which is a lot of fun, and we'll see what that means in a second, but it is a lot of fun. So before we go into too much detail about JavaScript, I figured we'd start with just a quick lesson on distillation. If you've never heard of it or know what it is, it'll be pretty quick. So the goal with distillation, typically, we're talking about alcohol, or distillation can be used to purify water or to make gasoline. The goal of distilling alcohol is to extract as much ethanol, and ethanol is the stuff that makes us feel good or bad, depending on how much of it you have. That's the stuff that we want. So the goal of that is to extract as much ethanol as we possibly can from beer or wine. And to do that, we take advantage of this wonderful thing in physics that different components and molecules and chemicals have different boiling points. So essentially in traditional distillation, and this slide's kind of crappy here, but you get the basic idea, we pour a whole bunch of beer or wine into what amounts to basically a water heater, and we turn up the heat. And because these things have different boiling points, at the beginning of what's called our run, we have things that have low boiling points that are called the heads. The heads are really nasty. Things like methanol, ethyl acetate. You drink enough of that stuff, it'll at best give you a headache, and at worst make you go blind or die. So it's really, really bad stuff. But this is stuff that actually is contained in beer and wine. So normally what we do is we turn this thing on, the heads start to come off, and we wait for the heads to essentially be boiled off. We condense them back down into a liquid, and we throw it away. We basically get rid of it like toxic waste. Once that's done, then we get into what we call the hearts. This is the good stuff. This is the ethanol. This has a slightly higher boiling point than the heads. And when those come off, this is good. We want to keep the hearts. This is the part that we're in this for. Once that happens, then what we have left is what we call the tails. And the tails, depending on what you're making, we'll either keep or we'll throw away, or not really throw away. We'll keep it and probably redistill it later. But basically, the tails come last, and these have the highest boiling point. And these are the things that have actual flavors to them. They're not bad for you, but sometimes we're after flavor. In the case of whiskey, we want to give that whiskey flavor to it, and sometimes we don't. Sometimes we literally want to just make vodka, or what we call neutral grape or neutral grain spirits, and we essentially, don't put those tails into there. So it just depends on what we're making, whether or not we keep that. The interesting about traditional distillation, though, is we restart this every day. We wake up in the morning, we turn on our boiler, we let it run, the heads, hearts, and tails come off. 6 or 7 o'clock at night, we're finally getting into our tails. We shut the thing down, we clean it out, and we go to sleep, and we start the next thing the next morning. This would be like rewriting a piece of code every day for the rest of your life, which would not be a lot of fun. So traditional distillation, if I had to put it in terms of what a programmer might understand. It's a synchronous process. You have to do A before you can do B, before you can do C. There's no getting around it in this traditional way. And really, it takes an immense amount of time and actually babysitting, because there's no clear delineation of when it goes from A to B to C or heads to hearts to tail. The only way to really tell is by tasting it or smelling it, which can be fun as well, too, when you're distilling. But that's another story. So when we talk about distillation traditionally, as a company, we looked at that and say, we'd be put out of business if we had to do this for very long. It's a very, very strenuous process. So what we did is we said, let's do something different. And we built a still of our own making. It's called the Heising 330. The 330 is actually just completely randomly by chance. It produced its first drop of alcohol on March 30th at 3:30 in the afternoon. Go figure. But we felt it was aptly named after that. And what this still does is actually works on what's called continuous distillation. And there's the same basic chemistry of what's going on, but it's done in a synchronous process, right? Asynchronous good, synchronous bad. That's why we like Node.js. Essentially what we do with continuous distillation is we pump alcohol into it, so beer or wine, and we continuously pump it in. And then we set up essentially a really precisely and precariously, and think of that word later, maintained temperature gradient that actually separates the heads, hearts, and tails continuously at the same time. And so what's cool about this is we can literally turn this thing on, warm it up, and it'll run 24 hours a day, 365 days a year, the same way. We don't have to restart it every day, as long as there's a steady stream of alcohol into it. So this is really, really, really cool. So if this is so great and wonderful, like, why does anybody, why doesn't everybody use one of these things? Well, it turns out a lot of people do. They tend to look like this, though. The gasoline that you put in your car is traditionally made on a continuous still. A lot of the large alcohol producers use continuous stills, but they're extremely complex. And when I talk about this very precarious sort of temperature gradient that's been set up there, there's a lot of equipment and a lot of scientific stuff that goes on to create that. And so it's very, very difficult to create a continuous still. But we were able to build one for a fraction of the cost. And so how do we do that? Well, number one, I think probably primarily is we were able and willing to embrace open source. Most people in the industrial control world don't like to use things that haven't been around for 50, 60 years and have been tried up in space, right? They want something that's tried and tested, but we were willing to take a little chance on that. This new, what I would call maker technology, but the idea that we can buy microprocessors and temperature sensors and barometers and things like that from SparkFront or Adafruit for cents on the dollar, whereas that stuff just didn't exist even 3 to 4 or 5 years ago. Just you couldn't do that. So there's this whole new set of technology that's out there that wasn't available. And I think probably most importantly, naivety is a really good thing to have. And really anything that you do, right, in any business, if you really knew how hard it was going to be to get into it, you probably would never start. And so the textbooks say that you can't build a continuous still at this scale, but we were naively thought that we could do it, and it turns out that you can. So when we did this, we ran into a few challenges, and we challenged ourselves to do a few things. Number one, we're in uncharted territory here. Again, the textbooks say you can't build a still of this size or for a company of our size without investing millions of dollars into it. So there's really no textbook to go after and look for this stuff. Number two, this is a prototype still, and we had to build it from nothing, but we also had to run it in a production environment. So it wasn't like we could be taking this thing down all the time and restarting it. And so if it's not running, we're basically losing money. And then, last but not least, this is dangerous stuff that we're working with. I mean, alcohol is extremely flammable. We're dealing with high voltage currents. We're dealing with liquids. We're dealing with pressure. We're dealing with liquids that will burn the skin off your face off. I mean, this is really nasty stuff. And so it's important that we realize early on is this is a dangerous thing, and so we have to be very careful with it. So we built this control system in order to basically do this. We had to build something on our own. And you can actually see part of it right here. We started with really cool machine right here. This is called a PC Duino. it makes the Raspberry Pi kind of look like a toy. It's got a gigahertz processor in it, dual core, a gigabyte of RAM, 4 gigabytes of onboard flash. It's got Wi-Fi. This one doesn't have it, but $50 to $60, $80 for something like this. It's amazing, and it's also Arduino. This one isn't, but the new versions are Arduino pin compatible too, so you can use Arduino shields with it. Really, really cool computer. Then we built a custom circuit board, and this is a printed circuit board that I designed and put together, and essentially it just snaps onto here. And this essentially creates all of the connections from this to our different sensors, which we have over 10 digital temperature sensors in this thing. We've got a barometer on this thing because the boiling point of liquids changes with atmospheric pressure, so we actually have to take that into account. And then we've got these really cool 240-volt power controllers and pumps and all those kinds of things. So we built this system pretty much from scratch. And essentially how it all fits together is that we've got Node.js running, and it's kind of cut off there, but it runs on this PC Arduino, which runs Ubuntu. And then through Fuse, or the file system and user space, we essentially communicate with these different sensors and controllers through the file system. And so serial protocols, I2C, SPI, general purpose input and output, connecting to different integrated circuits on the board, which then actually does things in the real world. So that's probably kind of cool and fun. So one of the questions we get asked a lot is, why did you choose Node? And I have to admit, before I started this project, I really didn't know much about Node, and it's a few years old now, so I know a little bit more about it now. But one of the reasons why we looked at it is just NPM just rocked. I mean, we really looked at this and we said, gosh, there's so many great pieces of code that are written out there, and it's so easy to bring in there and import it, and it was just beautiful. So we're like, cool, NPM, very cool. When we started out to build this, we really didn't know what we were going to put it on. We didn't know if it was going to run on a PC, if it was going to run on a window, you know, or whatever. So we liked the fact that it ran just about anywhere. It's also what I would call web forward. It's probably a bad term for it, but we wanted this thing to be very easily controllable with the web browser and from your phone and from your iPad. And, you know, network connectivity and web connections were sort of a first-class citizen in Node. We didn't have to add all this weird shit to make it work. And last but not least, I hate Python, I really do. That's a personal discussion for later, but a lot of people actually probably would have implemented this in Python. It's a great language for robotics and things like that, but we just decided it just wasn't right for us. So here's some interesting things we faced when we learned how to build this thing. Interestingly enough, Node.js and Linux file system actually isn't fast enough for some embedded protocols. So for example, OneWire is a really cool protocol that literally uses one wire to communicate with potentially hundreds of different devices that are out there. But it requires really, really super fast microsecond timing, and what we call bit banging on general purpose ports didn't work with the Node.js, so we needed to have it, it just wasn't fast enough to generate the signals that needed to be generated on there. Another interesting thing is we couldn't just reset press the restart button when there was a problem, because sometimes in most industrial processes, it actually takes a long time to heat something up or to get it up into a running state. And if you have a problem in your code, you can't just say, oh, I'll just reset it, get it running again, and we'll figure out the bug later. Resetting for us actually costs us 2 to 3 hours worth of time. So if we have to reset it, we've got to start over basically again. Now once it's up and running, it runs for a long time, but that setup process takes a long time. So that was an interesting thing that we faced. And this one is kind of interesting, and I say it breaks, but when it doesn't, it's really bad. And that's not a typo. Actually, when things break in your industrial control system, like a temperature probe goes offline, that's actually really easy to solve, right? If it goes offline, I shut everything down and I say, whoa, there's a problem. It's when something sort of breaks but doesn't really break is when it becomes a real problem. So for example, you have a temperature sensor that always reports that it's 50 degrees, and your heater is trying to say, okay, well, heat that thing up, heat that thing up. Next thing you know, it's a 3-mile island, you've got meltdown and all those types of things. So that's really, really bad. And that's an interesting problem that we run into. So we almost want stuff to break really, really hard. When it doesn't break is when it actually becomes an issue. So some different ways that we solve this, the speed issue with Node. Some of it was taken care of by writing native modules in C, C++. That helped a lot of it. A lot of it, too, was just pulling it off into external integrated circuits that handle a lot of that. That was a pretty easy thing to do. You know, the restarting issue, just a lot of code in there that you normally wouldn't have to write for a server program. We had to add is to resolve problems, to try to restart things a few times and maybe try to restart subsections of things to try to get it up and running before we notify somebody that something's wrong. And then watchdog programs, you know, things that actually just sit there and say, okay, has this value changed in like 20 minutes? If it hasn't, maybe there's a problem. Safety checks and things like that. So again, not a lot of things that you think about when you're developing server software, but things that were really sort of important to us. Else, really bad things happen. So as part of this, we wrote a sort of, I guess I'd call it a framework or a tool set called Node30. And what Node30 is in a nutshell, it takes care of basically all of the housekeeping in an industrial process. And number one, makes it really easy to connect and interact sensors, so things that bring in data, to controllers, things that control things like heaters and stuff, providing run loops, things like unit conversion, PID loops, if you're not familiar with those, process integral derivative. PID loops basically power everything from the thermostat in your house to rocket ships, I mean, or the cruise control in your car. So really important stuff, and it takes care of all that. And I think sort of last but certainly not least is make it extremely easy to expose that data to the internet or to a console and to be able to control it. So what I want to do is do a quick demo. And of course, by just saying that word, it probably won't work, but we're going to try it here. I guess actually you can sort of see that, but I'll zoom in here. So what Node30 does is actually pretty simple on the outset. Anybody who's built a, I guess you can't see it up there, hold on. Who's built a Arduino project will probably recognize this pattern right here, right? It's basically a setup function, and then down below we have a loop function. In this case, this loop function doesn't execute at system time. It actually basically just executes every second, because normally in industrial processes, you're not worried about like super millisecond, you know, calculations. It can take a little bit of time. You can change the timing on that. But there's some other interesting things that go on here. One thing you'll notice is there's no variables defined other than in our function calls here. And what's interesting, what we did about this is we didn't want to do a bunch of setup with variables or what we call in this case components. And I think of a component like a virtual representation of something physical, for example, like a switch or a sensor or a PID processor. And the simple fact of defining it in the function protocol, giving it a name switch, automatically defines it as a switch, literally an on-off state. So it's actually injecting that object into there as a switch with an on-off state. Anything with the word temp in it will be defined as a temperature sensor that converts back and forth between Fahrenheit or Celsius. And then anything with the word PID in it gets defined as a PID loop. And so it's probably an interesting way of doing it, but it really allows us to easily define things very quickly without having to create new classes, you know, and new everything and put it on there. So by the simple fact of declaring it there, it's been defined. The other cool thing about what we do is we have this concept of what are called viewers. And viewers are just basically what it sounds like. We have a console viewer which just outputs the various data to your console, which is, you know, fun and wonderful and interesting. We have a REST viewer, which exposes a real simple API that you can plug into. And we've got a web viewer, which actually builds user interfaces for you on the fly that you can actually control these things with. And then we can determine down below that if we want to expose it to the viewer or if we want to hide it and things like that. So what I've got here is a basically simple program. You could actually use this out of the box to power like a sous vide machine or a heater or something like that. We have essentially a run switch, and we see if that's turned on. And if it's on, then we tell our PID loop, we say, okay, this is the set point that we want you to go to. So that's something that the user inputs. and then our PID gives us a control value back, and the control value is sort of an arbitrary value, but think of it as somewhere between 1 and 100% that we want to turn our heater to. And then since I don't have a temperature probe and a heater up here, I just sort of simulate that temperature change. So what's cool about this is just to run this now, we can, we started, it gets up and running. Here we have our console viewer. Let me get out of here. And then if I want to go, I can refresh this. Here's my API that's exposed for me. I can get all the data here if I want. If I go back in here and, well, let me skip over that a little bit. And then if I refresh this page here, I actually have my web interface into this, and it's literally automatically defined this for me. In fact, if I turn on and off my run switch here, I can go back and see that it's been updated here. And what's also neat about this is I can also take data and graph it. So for example, let's say I want to graph this temp sensor here, and I want to set my temperature to 50 degrees Celsius, and let's go ahead and turn that run switch on, and we'll actually see that it's going to run a simulation in this case, but this, this would be a real feedback loop of trying to set the temperature in my system here. It's going to overshoot it like a typical PID, but then it's going to try to basically come back and get somewhere close to 50 degrees. And so that's typically what you see in a I mean, this, like I said, it could work as a sous vide machine, it could work as a heater, it doesn't really matter. You can see it, trying to reach a new temperature here. And I literally wrote all this with just a couple lines of code. Now, what I want to finish up with, though, is another cool piece of this, which is connecting it to the internet. One of the things I do in my day job is connect things like stills to the internet and make it very, very easy to sort of view this. So you can see I've added this Dweet viewer, and if I go ahead and stop here and run that, it's going to be the exact same program here, doing the same sort of thing, but let's go ahead and set this to 50. I'm going to return this on. But if I go to dweet.io, and anybody can do that, you can literally go here right now and look at it, /follow/CascadiaJS demo, I can actually see this value being updated in real time. And this is something that's been published to the internet that anybody can take and bring in. And where this goes even more interesting here is we can go into what's called FreeBoard and actually create a dashboard based upon that data and pull that directly in. So we allow our users to take any data that they want from this still, play around with it, and do anything that they want with it. In fact, if you take it to its sort of next level, this is actually our still running in Washington right now. It's actually a camera of it running in there. Nobody's in there right now because they don't need to be, but we've got ambient pressure that's been going on here. We've got the different heaters, and all of this is being updated in real time, and anybody in the world can access this and view it. In fact, we've even had ideas of literally being able to say, I want to order the next gallon of alcohol that comes out of this still and be able to order it right there. I don't know if it's legal, though. So to finish up here, just kind of a quick demo of what we can do with it. But I think in conclusion, what's really neat about this is, Node.js actually does make a really good, excellent system and reliable system for industrial processes, something that we really didn't know much about it going into it, but have come to really trust it and really understand that it can actually do what we want. So that's it for me.